This video describes the design and basic operation of traveling wave tubes. Traveling wave tubes, abbreviated to TWT, pronounced TWT, are vacuum tubes used as high-gain, low-noise, wide-bandwidth microwave amplifiers. In older literature, TWTs are called O-type microwave tubes. These are linear beam tubes. This means the magnetic field is in parallel with the DC electric field. There are two basic types of TWTs. The Helix TWT is a relatively low-power device, usually operating in the tens to hundreds of watts range, and capable of broadband operation, over 2 octaves. The bandwidth of 1 octave is reached when the upper cutoff frequency is twice as large as the lower one. The coupled cavity TWT can handle powers of megawatts, but its bandwidth is limited to about 10 to 20%. Conceptually, the electron gun, electron beam, and collector are the same for all TWTs. However, there are significant differences in the RF circuits. Despite these differences, the operating principles remain the same. In this video, we will focus on the operation of the Helix TWT. The graphic shows the electrical design required for operation. All traveling wave tube components, including the electron gun, the RF interaction section, and the collector, are kept in a high vacuum. The vacuum envelope is evacuated to the 10 at the power of -9 millibar range. Metal, ceramic brazing technology is used for the electrical feed through to the electron gun and collector, as well as for the windows at the RF input and output. The electron gun is similar in construction as in all cathode ray tubes. It consists of an indirect heated cathode that must be heated to a temperature between 850 degrees and 1100 degrees Celsius, 1500 degrees to 2000 degrees Fahrenheit, to produce appreciable electron emission. A focusing Wennet cylinder with the same potential as the cathode, or a small negative bias up to -20 volts relative to the cathode, directs the electrons in the desired direction. One or more anodes are used to generate the requisite electron velocity. In most cases, the Helix also has a more positive potential than the cathode and acts as an additional anode. The beam passes the anodes through a hole or a grid and travels through the slow wave structure and the surrounding magnet. The surrounding magnet provides a magnetic field along the tube's axis to concentrate the electrons into a narrow beam. This magnet can be a permanent magnet or an electromagnetic focusing element such as a solenoid. A permanent magnet does not require a power supply and ensures that the magnetic field is always present. However, it does not allow for an adjustment of the strength of the magnetic field to optimize tube performance. If a single permanent magnet is replaced by several smaller magnets, the size and total weight of the magnet structure are reduced. The housing is typically made of aluminum to prevent the disruptive influence of ferromagnetic materials. External magnetic materials can interfere with the uniform magnetic field and damage the traveling wave tube. Therefore, the packaging of a traveling wave tube often has oversized dimensions. Since the electron beam into the tube travels slower than the speed of light, there must be some means of slowing down the forward velocity of the electromagnetic wave. The electron beam speed of a TWT is about 10 to 50% of the speed of light. The speed depends on the cathode voltage that may be between 4 to 120 kilovolts. The slowdown is done through a slow wave structure, on which the electromagnetic wave propagates. The collector in a TWT is a voltage electrode that has the same potential as the body of the tube, which is usually grounded. The other electrodes have a high negative potential in comparison. When there's no input signal, all the energy of the beam needs to be dissipated in the collector. To handle the heat at high power levels, forced air cooling or liquid cooling of the collector is necessary. High-power TWTs often use multi-stage collectors, as shown in the figure. The slide shows the power supply arrangements for a typical helical TWT. The beam current is controlled by the grid cathode voltage. This grid can also be used to block the tube with a negative bias and thus realize a pulse mode completely. The blocking voltage is then superimposed with a positive square wave pulse. The circuit that drives the control grid is usually referred to as a grid modulator. In modern TWTs, the beam focusing is preset and no adjustment is necessary, but if the focusing is adjustable, the tube should be run initially at a low beam or collector current, and the beam focusing magnets adjusted for minimum helix current. The helix voltage should also be set for minimum helix current. In the following description, we will follow the electrons from emission to collection. For the helix TWT, it helps explain the RF behavior to first consider a single wire transmission line above a ground plane. If the RF generator is on the left end of the transmission line and if a matched load is on the right end, then the charge and field patterns move to the right with constant amplitude. Electric field lines extend from regions of positive charge to regions of negative charge. The velocity of propagation is that of light and is independent of frequency. A pattern of the RF magnetic field is not displayed or taken into account because the RF magnetic forces on the electron beam in the microwave tube are insignificant compared to the forces generated by the electric fields. Next, assume that the single wire transmission line is formed into a helix. 2 complete turns or pitches are required for each half wavelength. With the helix, the axial signal velocity, v, index p of the RF signal is approximately the speed of light multiplied by the ratio of the distance between the windings, the so-called helix pitch, to the circumference of one winding of the helix. In the center of the helix, the electron beam from the electron gun moves toward the positively biased collector. The high voltage potential between the cathode and collector causes the electrons to move. The electron beam is focused by the strong permanent magnetic field. The magnetic field prevents the electrons in the beam from repelling each other. Without any high-frequency input signal, the electron beam maintains a uniform density and speed of electrons. The speed of an electron in the beam is the square root of the electron charge 2e. E is 1.602 times 10 to the power of minus 19 coulomb, divided by the mass of an electron. M is 9.109 times 10 to the power of minus 31 kilogram, multiplicated with the anode voltage Va. When an RF signal is applied to the left end of the helix, it will travel at a velocity close to the speed of light in a helical path along the conductor. The average velocity in the axial direction, known as the phase velocity of the helix, usually denoted by v with the index p, is the velocity in the helical direction reduced by the pitch of the helix. Electric field lines extend from regions of positive charge to regions of negative charge with a configuration similar to that shown for the single-wire transmission line. Other than the reduced velocity, the primary difference between the field pattern for the helix and that for a single-wire transmission line is that there is an electric field inside the helix with large axial components. The forces on the electrons would be directed toward the positive region and away from the negative regions. The field pattern would vary sinusoidally in the axial direction. If the axial velocity of the electric field caused by the helix and the beam is nearly the same, then electrons will experience a continual force toward the positive region as the beam travels through the helix. This local electric field has a relatively large influence on the electrons due to the inverse square law. It is superimposed on the voltage potential from the collector, which is still distant. The axial electric field components accelerate some electrons and decelerate others. The increase in electron charge ahead of the region and decrease behind the region produces an electron bunch. In the negatively charged region of the helix, the areas of acceleration and deceleration are reversed, reinforcing the effects through the positively charged region. The deceleration in this picture points to the same point as the acceleration in the previous picture. Both forces cause an accumulation of electrons to form the electron bunches. The bunches of electrons that gather in the beam push away the electrons on the helix, causing those electrons to move both to the right and the left. The electrons on the helix move at the same speed as the bunches in the beam. In relation to a moving bunch, the electrons on the left move to the left at twice the speed of the bunches. This creates a deficiency of electrons, making the circuit positive. Concerning the moving bunch, the electrons on the right, which are moving at almost the same speed as the bunch, are nearly standing still. As a result, electrons gather in front of the bunches, creating a negative charge in the circuit. The energy extracted from the electron beam in slowing electrons to the bunch velocity is transferred to the circuit field, thereby producing amplification of that field. The mutual interaction of the beam and circuit results in an exponential growth of the circuit voltage. The input voltage is decreased using an attenuation area to prevent feedback and reverse operation. This process reduces the oscillation on the helix to nearly zero, allowing all input energy to be transferred to the electron beam. Common forms of attenuation include coating the support rods of the helix with a lossy material or using a helix made of a conductor with a higher specific resistance. The transitions must be gradual to avoid reflections caused by the change in impedance. In addition to the spiral helix already shown, other types of slow-wave structures can also be utilized. A contra-wound helix uses two helices wound in opposite directions. Both helices must be identical in dimensions. Both helices have electrical contact at the crossing points, forming a circular conductor that lies at a slight angle in space. A contra-wound helix is less sensitive to backward wave interactions and therefore allows higher operating voltages, currents, and power. The penalty for these advantages is that the bandwidth is less than that of a single helix. A ring loop TWT uses loops as slow-wave structure to tie the rings together. These devices are capable of higher power levels than conventional helix TWTs but have significantly less bandwidth of 5 to 15% and a lower cutoff frequency of 18 GHz. The feature of the ring loop slow-wave structure is high coupling impedance and low harmonic wave components. Therefore, ring loop traveling wave tube has the advantages of high gain, 40 to 60 decibels, small dimension, higher operating voltage, and less danger of backward wave oscillation. The ring bar TWT was developed from the contra-wound helix and has got the same characteristics likely the ring loop TWT. This one slow wave structure is very easy to make by precise laser cuts in a thin copper pipe. In coupled cavity TWTs, several tens of klystron-like cavities are used for the slow wave structure. The electron current flows through these resonators, which have alternating slots, creating a coupled line. The RF path travels in a zigzag pattern through the coupling slots in the resonators, constantly crossing the electron current. The high quality of the single resonators allows the coupled cavity TWT to have a better upper cutoff frequency, resulting in a significant increase in power. However, the tube also has a very narrow bandwidth due to the frequency-dependent resonators. Coupled cavity TWTs can provide over 100 kilowatts of pulse power and around 25 kilowatts of continuous wave power. The folded waveguide, abbreviated to FWG, is a rectangular waveguide folded in a serpentine shape to reduce the axial phase velocity of the electromagnetic wave, allowing it to synchronize with the electron beam. It consists of a bent waveguide with a circular beam tunnel. Compared with the helix slow wave structure, the folded waveguide TWT has a narrower bandwidth and lower interaction impedance but can provide higher average power handling capability since it is a full metal structure. Folded waveguides can be machined into a brass block as left and right halves. This technology enables the miniaturization of the slow wave structure for amplifying frequencies up to the terahertz range. Usually, a folded waveguide TWT is designed to work with beam voltage in the range of 10 to 20 kV. In a TWT, there is only voltage amplification. Since the line impedance remains constant, higher voltage results in a larger current, leading to increased power. The attainable power amplification is essentially dependent on the power input. See diagram. As shown in the diagram, the gain of a given TWT has a nearly linear characteristic of about 27 decibels at a small input power. If you increase the input power, the output power doesn't increase for the same gain. So you can prevent saturation of the following mixer stage in the radar receiver. The relatively low efficiency of the TWT partially offsets the advantages of high gain and wide bandwidth. The maximum output power specification of traveling wave tubes refers to the point of saturation, known as saturation power. The power amplification also depends on constructive details, example given, the structure and length of the helix, and the electron beam diameter. This one is adjustable by the density of the focusing magnetic field. It depends finally on the anode voltage UA2. This is the DC voltage on the helix. The extremely broad bandwidth of the helix is the single most important property of this circuit. No other circuit has ever rivaled the helix in bandwidth, and most do not even come close. The diagram illustrates the maximum output power at the respective saturation point of a given helix TWT. One of the most beneficial features of TWT amp is its high bandwidth and relatively low noise figure, which have contributed to its widespread use. The typical efficiency of the TWT amp is about 10%, though some modern tubes may reach 40%. The traveling wave tube exhibits good noise performance, but distortion increases significantly near the saturation point. Electron tubes are generally unaffected by strong cosmic radiation. Semiconductors can lose their properties depending on the level of radiation exposure. A traveling wave tube amplifier whose output drives an antenna is a type of transmitter. They are commonly used as amplifiers in satellite transponders, where the input signal is weak, and the output needs to be high power. Traveling wave tube amplifiers used in satellite communications are considered reliable choices and tend to live beyond their expected lifetime of 15 to 20 years. A TWT, essential for transmitting data on the Voyager 2 spacecraft shown in the picture, is still functioning after over 45 years. Launched in 2021, the James Webb Space Telescope makes use of Ka-band TWTs. For example, the table shows data from some traveling wave tubes for satellite communication. The traveling wave tubes, utilizing a helix as a slow wave structure, can be identified by their high bandwidth. In the millimeter wave range above 40 GHz, folded waveguides are predominantly used. Traveling wave tubes with coupled cavity slow wave structures are used as power amplifiers or as preamplifiers for high power transmitters with crossed field amplifiers or amplitrons. They have significantly higher output power but a lower bandwidth of 10 to 20%. The figure shows some of the total 128 coupled cavity TWTs used in the AN/FPQ-16 radar in North Dakota operating in VHF band. Traveling wave tube amplifier transmitters are used extensively in radar, particularly airborne fire control radar systems, and in electronic warfare and self-protection systems. In smaller radar sets, a single TWT is adequate as a power amplifier, as the SkyGuard transmitter exemplifies. The TWT supplies power to the independent search and the tracking antenna through a power splitter. I hope you enjoyed watching the video. Thank you for your attention.